Good morning, everybody, and thank you for this invitation. My name is Thorsten Knipfer. I'm an assistant professor at the Faculty of Land and Food Systems at the University of British Columbia, and I want to talk to you today about the triphasic water potential curve as a cost-effective tool to predict stormwater closure and turgor loss point. Before I get into the details, a couple of words about our location. The University of British Columbia is located on the Point Grey campus on the unceded and traditional territories of the Musqueam peoples. And if we go outside of Vancouver, we encounter an agricultural region where we find crops such as blueberries, hazelnuts, poplars as wind shelters, but also corn. Some of those crops I will address later on in my presentation. The agricultural region around Vancouver also experiences current challenges from climate change. We, for example, had extreme flooding events in 2021 that made it very difficult to prepare the fields for the summer season. But we're also experiencing extreme dry conditions during the summer month related to reduced precipitation and reduced snowpack in the winter. In order to tackle those type of challenges, we are investigating in our laboratory the window of optimum crop performance to identify ways of how we can manage plants with less irrigation water and more precisely. What you can see on this diagram is an illustration how physiological responses happen when the soil is becoming drier and the stem water potential or the water status of the plant declines. If we go from the left to the right and we leave this optimum window of crop performance, we will encounter responses such as stomata closure, dehydration of roots, the water release from tissue internally from the plant that is sourced through the transpiration stream, the loss of turgor in leaves resulting in leaf wilting, the collapse of leaves inhibiting gas exchange and photosynthesis, and ultimately the formation of air embolism in the water transport system, blocking movement of water nutrients to the canopy. If we go to the left-hand side, and we ask ourselves responses under too wet conditions. We can see here when the soil is becoming too wet, waterlogged, the roots experience anoxic conditions, may form parenchyma, and exhibit cellular modifications that alter plant performance. So our goal here is to identify thresholds with regards to the stem water potential to be more efficient in our management of irrigation water. So how do we measure stem water potential? It can be done fairly easily. Many plant water relations laboratories around the world have a so-called shoal under pressure chamber in their laboratory. In order to take this measurement, we would bag a leaf, as you can see here with a plastic bag. You let it equilibrate with the stem, and then you cut off this leaf and you place that leaf with the bag into the pressure chamber. You slowly raise the pressure in the chamber until water will emerge on the cut surface of the leaf, and that will represent your stem water potential. The stem water potential is equivalent to the pressure that needs to be overcome that exists inside the leaf related to the tensions of water in the leaf. So if we look now in more detail at the stem water potential can be measured any time of the day as any other parameters. And typically it's measured midday when the plant experiencing most stressful conditions. It can also be measured pre-dawn when transpiration rates are relatively low. This relationship here shows you that if we would relate midday and predawn water potentials, we get a fairly linear relationship. The example here is for grapevines and is published by Williams and Arroyo in 2002. In 2023, we published a paper also on grapevine, and we observed that this relationship is not simple linear, but exhibits nonlinear behavior. As you can see here on the left-hand side, that can either be a triphasic response, where you have three phases that are separated by two distinct boundaries. Or to the right side here, you can have a biphasic response where you have two stages that are separated by one boundary. These two examples here are shown for Syrah to the left and Cabernet Sauvignon to the right. When we ask ourselves what is the physiological significance of these boundaries, we can compare those boundaries from our triphasic water potential curve to measurements such as stomatal conductance. You can see here in the top panels that stomatal conductance declines with a reduction in predawn water potential or an increase in soil dryness. A minimum value of stomatal conductance for Syrah was reached at 0.81 megapascal. If we compare this to the bottom panel of our triphasic curve, that matched pretty well with our first boundary of 0.98 megapascal predicted from the curve. Similar for Cabernet Sauvignon, we saw that a value of negligible stomatal conductance was reached at 0.74 megapascal. That matched pretty well with our threshold predicted from the water potential curve at 0.8 megapascal here. These kind of triphasic responses have also been observed in other woody perennials. In 2020, we published a paper that was focused on walnuts. And you can see here that also in walnut, we see this triphasic curve, three phases separated by two boundaries. If we compare these responses again to measurements of stomatal conductance, we see here that stomatal closure or a value of stomatal conductance close to zero was reached at the boundary between phase 1 and 2 of our water potential curve. Similarly, we see these triphasic response curves for almond. Midday water potential, however, is not just responsive to soil dryness, but also to the atmosphere. And if we want to have the water potential curve as a tool for irrigation management, we need to normalize and correct for these atmospheric effects. So in this diagram here is just a short illustration that demonstrates you that water molecules in the plant, they are connected over hydrogen bondings. Here it's illustrated in form of a chain of pearls. If we have, for example, then dry soil conditions, but still a humid and cold atmosphere, there would be a stretch within those water molecules. But in turn, we can also have a similar stretch in these water molecules if we have wet soil conditions and a dry atmosphere. So the goal here was then to correct for the impact of air vapor pressure deficit on our measurement of midday water potential. You can see in this diagram two scenarios that illustrates you the response of midday water potential to changes in vapor pressure deficit. The open symbols in that graph represent wet soil conditions. Midday water potential under wet soil conditions is closer to zero than under conditions of high VPD conditions, resulting in that slope value or the so-called stem water potential baseline. Similarly, if you would have plants under constantly dry conditions and you would go from a low to a high vapor pressure deficit, midday water potential declines. So in essence, you can achieve a similar value of midday stem water potential either under high or low vapor pressure deficit or under high and low soil moisture conditions. So we can correct now for this vapor pressure deficit effect by establishing ourselves a relationship of midday water potential with observed vapor pressure deficit that is measured at the same time, as you can see on the left-hand panel for hazelnuts. This relationship here provides us parameters that gives us indications about the y-intercept A and the slope value B. So if we know our vapor pressure deficit, we can calculate our expected value under well-watered conditions and subtract that value from our observed value, our midday water potential, to arrive at a so-called delta psi midday, or a corrected midday water potential. The right-hand side panel illustrates that in more detail by doing this correction of our midday water potential for fluctuations in vapor pressure deficit. We basically move all our points here to the similar line or place up here and reduce this variability in that response. So if you look at our data that we then collected for hazelnut trees, we can see again, if we have our corrected delta psi midday on the y-axis and our predawn water potential on the x-axis, again, we see a triphasic water potential curve with a boundary value of minus 1.05 megapascal separating phase 1 and 2, and another boundary value at minus 1.99 megapascal separating phase 2 and 3. We compare that to our responses in stomatal conductance. We see that our stomatal conductance reaches a value of close to 0 at minus 1.16 megapascal. That's very close to our first boundary threshold from our water potential curve. We also, in this case, measured the turgor response at the leaves. And we can see here that the turgor in the leaves declined with a decline in predawn water potential, reaching 0 turgor at minus 2.23 megapascal. That again matched closely with our second boundary of minus 1.99 megapascal from the water potential curve. We also confirmed our turgor loss point values here from measures of turgor loss from pressure volume curves that are represented by these squared symbols in the right-hand side graph. We have used the water potential curve as a tool for physiological phenotyping and characterization of functional traits such as stomatal conductance and turgor loss. We have employed a mini weighing lysimeter platform in the greenhouse to also measure responses of evapotranspiration, or ET, that we related to our stomatal conductance and water potential measurements. You can see here that our water potential curve thresholds also matched very well with our thresholds derived for our ET curve on the bottom panels. Again, water potential curve seems to be a cost-effective tool for physiological phenotyping in the future. Recently, the lab of Felipe Barrios Macias at the University of Nevada also explored that relationship of midday and predawn water potential for melons as a non-woody species. And they also found that That relationship of predawn midday water potential is not simply linear and exhibits a biphasic uh, shape. And the boundary that was determined here from that characteristic was again uh, related to the change in stomata conductance as expected to the drying soil and the reduction in predawn water potential. So the takeaway from this is that in general, the relationship of predawn and midday water potential is not simply simple linear, as you could see here for woody perennials, such as grapevine, walnut, almonds, hazelnut, but also other non-woody species such as melon. And the water potential curve appears to be a cost-effective tool to predict thresholds of stomata closure and turgor loss point, that especially if you don't have access to an expensive gas exchange systems or other tools in your lab. If you want to review more information about that, I would direct you to our recent paper of Bristow and Knipfer in 2025, published in Plant Physiology. Before I end, I want to acknowledge our funding agency, NSERC, the Canada Foundation for Innovation, the Canadian Light Source for providing access to X-ray imaging, the BC Hazelnut Growers Organization, and the Faculty of Land and Food Systems, as well as lab members Stephen Bristow, Michael Bielek, Shine Ju, Lucas Stöckel, and James Lau. Thank you very much and have a good day.